All right, looks like we're up and running now. We're going to continue with chapter 5. Again, we're going over this book right here, No Nonsense Quantum Field Theory, by Jacob Schwittenberg, and I think I've been pronouncing his last name wrong, but anyways, we are going to continue with the Lagrangian for the Klein-Gordon equation, right? So previously we talked about how the Klein-Gordon equation, what the Klein-Gordon equation means, and we found out that it was a way to model scalars sort of attached to each other by springs. So let's write down this Lagrangian again. I'm going to go ahead and write down this Lagrangian. I'm going to do it in black. So this is our Klein-Gordon Lagrangian. And we've established in the previous video that over a continuous space of a scalar field, remember the Klein-Gordon equation applies to scalar fields in three-dimensional space. This is how we do this. So we're taking an integral over three-dimensional space. We do 1/2. This is just I'm just rewriting the Lagrangian we've established before, like this. So we have a kinetic energy of our oscillators minus the potential energy stored in each spring, and then minus the potential energy that's stored So we have the potential energy of each particle, and then that's this right here. And then the potential of the spring that's associated with the spring that's coupling the two is, as we've seen in the last video, goes as m squared with that squared. So this is our Klein-Gordon Lagrangian that we've established before. And we were able to realize that this was roughly analogous to something that looked like this, where we have 1/2 mc squared d mu phi d mu phi minus 1/2 m, or 1/2 k squared, k, not squared, but that's like this. This is also our Klein-Gordon Lagrangian, just written in a different way. We sort of absolved this and this into this four derivative, or these two four derivatives. And then this here becomes this. And what's interesting, the book notes this, is that m, in this case, is synonymous with k, with the constant k, or it's something of a proxy for k. And the book notes, again, that you can imagine what might happen if m increases. If m increases, then that means our k is going to increase as well. And what does k physically tell us when it comes to understanding springs? Well, it's something that tells us about how stretchy the spring is, right? So if m increases, so if the mass of the particle that we're considering increases, if m increases, then that would lead to a harder means to excite or more difficult means to excite the scalar. So I'll just say harder to excite. I spelled that wrong. Okay. So this is sort of a brief rundown on what we did before, and we're noticing that the mass of the scalar that we're considering is synonymous with the stretchability of the coupling between the two. Also recall that when m is 0, right, so if m equals 0, the phase velocity of the plane waves are all the same. Now, this is something we talked about when we were talking about waves back in chapter 3, I believe. The phase velocity of the plane waves are all the same, but when m doesn't equal 0, the phase velocity depends on the wavelength. So, and again, that was something that we talked about in chapter 3. So, the phase so like that. So if m equals 0, the phase velocity of the waves are all the same. And if m doesn't equal 0, then the phase velocity depends on the wavelength. So the phase velocity is proportional, or is a function of the wavelength. So phase velocity depends on the wavelength. Again, that was something that we talked about sort of in depth back in chapter 3. So let's continue here. So the book then sort of, it doesn't diverge, but it talks about something very interesting where we could consider now the potential. So last time we considered the potential of coupled springs, right? So, or scalars that were coupled together via springs. That was the picture that we had in our mind that we were using to develop our Lagrangian. Let's consider now a different looking potential, right? So the potential that we had initially was 1/2 k phi squared. That was the potential of phi. This was for a spring. Okay, well, what about, let's consider a different type of potential. Let's consider maybe the potential for a pendulum. So the potential for a pendulum, if you recall again from classical mechanics, again, if you don't recall, then this is what it looks like. It looks like 1 minus cosine this. So this is for a pendulum. It becomes a little bit more difficult to imagine to picture what this might look like. But we don't necessarily have to picture. We can just say, well, this is what the potential might look like. We could propose a potential. Perhaps if we had coupled potentials, again, this is a potential that describes the coupling between two things, right? A spring oscillates just like a pendulum oscillates. So nothing should really be stopping us from thinking about, sorry, my dog is whining. Nothing should really be stopping us from thinking one should be used more than the other, right? Let's take a look at this. If we consider this for a pendulum, again, this is just an oscillating object. We can say, for example, Taylor expand this cosine out. And what do we get when we Taylor expand this cosine out? We get these even terms, like this, right? So this is still our potential for a pendulum. We're just rewriting it in terms of the Taylor expanded for the cosine. But what does that look like now? Well, these two ones will cancel out, and we get mgl times that minus or plus actually my bad, this is actually a plus right here because these two minus signs will multiply to become a plus, and then we have this minus right here. Okay. Well, if we so this is an approximation. Again, this is an approximation because Taylor expansions are always approximations of actual functions. I'm going to zoom up here. Well, what is this? Well, what can we do now? We can just multiply this out, and we get something that looks like this. Well, if you recall, we had, if you remember this right here, for our spring, we had some constants times the square of our value. Same thing right here. We have some constants times the square of our field value. So this is really just, this here is really just a modeling of a spring. But by considering the modeling of a pendulum, we've been able to get this extra term right here. And this is a first order approximation to the pendulum, right? Because we only went out, this is actually a second order approximation because we went, or it depends on how you count. You could start from 0 or you could start from 1, but this is an approximation to a pendulum of potential, and we got this term right here. Now, what does this mean for our Lagrangian? Well, for our Lagrangian, this means that for our pendulum, or for our Lagrangian, I'll just write L now is not just this, we have our constants here, but we can add our constants in our fourth order term. So this becomes a Lagrangian. Now this is very interesting, and it's believed, the book actually goes into this, it's believed that there are an infinite number of terms that play a role here. So we could, what we're saying here is that the spring is just an approximation to something that has an infinite number of potential terms. And the pendulum is sort of the way we get there, okay? And this will be important later. I can't remember which chapter it's in. I think it's like in chapter 6, where we'll talk about spontaneous mass creation. This is something that Lawrence Krauss, if you know who Lawrence Krauss is, he talks about. It doesn't really go this deep into it, but he talks about something out of nothing. Spontaneous mass creation will come out of this approximation term. And so that's very, very interesting. Let's consider quickly now the solutions to the Klein-Gordon equation before we call it quits. Again, sorry for the dog whining in the back. So the solution, so recall now that, okay, so this was our Lagrangian right here. This was our Lagrangian. This is another way we wrote the Lagrangian. Let's consider what the solutions might look like now. So the solutions have to obey, again, I'll write it like this. So now let's consider, we're going back to looking at the Klein-Gordon equation. Solutions to the Klein-Gordon equation. So recall that the Klein-Gordon equation was this. This was something we derived in the last video. We can propose that phi, again, it's a function of x mu. This exists everywhere in space, right? So here's a point x mu, and I should be able to tell you what the value of phi is at that point. And let's propose that phi of x mu is the following, or takes the following form: e to the minus I k mu x mu. Right, so we're proposing this. The reason we're proposing this is that when we plug this into here, what we get is that when we take the double derivative, we're really just getting this right, because when we take the derivative once, we get with respect to space, or with respect to its argument, we get k, right, because this is the coefficient that's in front of the argument. So we get k, and then we get k again when we perform another derivative, right? So these are the two k's we get, and we're following the up and down notation here. And what does this mean? Well, this if we were to propose, okay, so the book says something like this. We're gonna then propose, well, that this has to be a number, okay, because these are two vectors. One's a contravariant vector, and one's a covariant vector. So that's something we talked about in special relativity, right? These are objects that we fundamentally need to know in from special relativity. Well, when we sort of concatenate a vector with a covector, we get a number, and the number we're going to get here, we're proposing, is m squared. Okay, and so we get that 0 equals minus m squared plus m squared phi of x mu. Well, that's 0, right, because these are opposites of each other. So we get 0 times phi, 0 equals 0. That means that this form is a good solution to our Klein-Gordon equation. And that really is, that comes from the proposition that m squared is the inner product between the two the two k's, the two these two four vectors right here. Again, these two four vectors, they're related to the angular and the spatial momentum of the particle at that point x mu, right? So we can write this out. I'm not really close to 30 minutes here. The stipulation again is that k mu k mu equals m squared, right? So this means that w squared over c squared minus kx squared minus ky squared minus kz squared equals m squared, right? Because we're doing this multiplication, omega over c kx ky kz. So we have our covector and we have our vector, and that's going to give us m squared, like that. And so this again right here, this again is the proposition we're making. This is all equal to m squared. So we want to recall one more thing here, or not really recall something, but since we've proposed that that phi of x mu looks like this, well, what is this? This is a wave, right? If this is a wave, then theoretically any other wave should work, right? So say we could propose that e to the I, this, that should work also. Again, this minus sign comes from, actually, I think I misspoke earlier. This minus sign comes from the I, right? These I's. So these should work, right? So this is proposition number 1, and this is proposition number 2. Well, as we know, any combination of two waves is also a wave, and so that means any combination should also be a solution to the Klein-Gordon equation also. So how do we write this? We write this as this is the most general form of the solution to the Klein-Gordon equation, and it looks like this. Of x mu, so phi of x mu, this is a scalar on a field, looks like it's an integral over all the possible momenta. We're dividing by normalization factor, and we'll see why we do this later. This is just, for right now, it's just a constant, doesn't really matter. AK, or not A sub k, A k mu e to the I, or minus I, k mu x mu, plus b of k, k mu, e to the I, k mu x mu. This is our most general form. I'll box this. These are waves, right? This is a wave, this is a wave. These are just, right now, these are really just coefficients. So we could, they scale up the amplitudes of the waves, and we can add any linear combination of these waves basically with one another. These coefficients are functions of the momentum, right? So what this fundamentally becomes is you have these waves, and depending on what the momentum is at some point, you're going to get a value for A and a value for B, right? A corresponds to this right-going wave because of this minus sign, and the b corresponds to the coefficient of left-going waves, depending on how you define right and left, obviously, but one is fundamentally a different object than the other. And so this is the most general solution to our Klein-Gordon equation, okay? I'll note sometimes you'll see it written as this, where we have cubes and 2 omega k. So this is the angular momentum is involved. So we're taking out the temporal component and we're putting it in this normalization factor. But when we take out the temporal component, that leaves us with just summing over spatial components, like we're doing here. And we have the same deal, right? We have the same deal where we have A of k mu, E of I kx. Now we're assuming that we're just summing over the spatial components now, okay? Plus a dagger, where a dagger and b are sort of synonymous with one another. This is another way you'll see it. I personally like this way a little bit better because it has everything in it, right? Nothing's really concatenated or anything like that. But again, you'll come across this and it'll be useful to know that this is essentially the same as this right here. And so, yeah, this is, I'm coming up on 30 minutes now. And so this is the Klein-Gordon equation. So we've gone over now the Klein-Gordon equation, or what the book talks about when it comes to the Klein-Gordon equation. The next thing is going to be the Dirac equation. Now I think the Dirac equation is probably going to take 3 videos because the Dirac equation, there's a lot to it. There's a lot to it, and the book doesn't even go halfway into talking about it. It really, it goes into the essentials, right? But there's so much to the Dirac equation that I will talk about just what's mentioned in the book in this playlist, and then in a separate playlist, perhaps on a different quantum field theory book, if something different comes up, then that's where I'll have it. But there you go. That is the Klein-Gordon equation. Then we're going to talk about the Dirac equation, and then after that, we're going to talk about the Procco equation. And this is all in Chapter 5. Chapter 5 is a huge chapter, and we're going to feel so proud of ourselves when we're done with it. And we'll understand these are all free fields we're talking about, and yeah, free fields meaning that we haven't considered interactions yet. We're talking about all of this stuff and we haven't even considered interactions yet. Interactions are going to come when we start talking about Green's functions, and that's going to be fun. Interactions are that's where the stuff hits the fan, if you will. And so without further ado, I'll see you guys in the next one where we'll start talking about the Dirac equation.